We now discuss nets energy subsystems. Nets must supply sufficient energy to support all the passenger and goods movements provided by CUTs. This is broken into two parts, minimizing the amount of energy required and providing that energy for LAN and WAN in the form of renewably generated electricity. LAN and WAN would replace all CUTs, road, rail, and air travel within a landmass. This video shows that the LAN and WAN energy required is less than 10% of the CUTs levels. This is achieved by addressing all of the factors that affect a vehicle's energy consumption. These involve providing a propulsive force that overcomes the forces of air drag and rolling resistance, as well as that needed to perform accelerations. For all the vehicles, the propulsive force is generated by the vehicle's powertrain. The powertrains convert energy stored in a chemical or electrical form into a mechanical propulsive force. The efficiency of this conversion is the other big factor in the energy consumption. Electric powertrains are far more efficient than those which burn fossil fuels. We will first review the CUTs demands and then show how WAN and LAN achieve these savings. We conclude this with an analysis to determine the annual U.S. passenger and freight energy demands for all trips except air travel between landmasses. These images were created by the U.S. EPA. They indicate where the available energy goes for CUTs vehicles with electric, hybrid, and fossil fuel powertrains. This chart breaks down the energy consumption for each of these types in city and highway driving. The consumption ratios were taken from these images. The total energy for each category are averages taken from a set of about 200 vehicles for which we were able to obtain the EPA consumption rating, as well as energy demand-related vehicle parameters we will discuss shortly. The CUTs road vehicles store energy on the vehicle in some chemical or electrical form. For electric vehicles, the storage is in batteries that lose about 10% of the input energy during charging. WAN vehicles are battery electric, with similar charging costs. A motor converts the stored energy into mechanical energy that goes through a drivetrain that ultimately turns the wheels. For internal combustion vehicles that do not turn off their engines when stopped, there is also some small loss from idling. The powertrain, which includes the motor and the drivetrain, along with the idling losses, are the brownish-colored elements in the chart. WAN vehicles use small electric motors in the propulsion modules. The input energy also powers parasitic devices like alternators that are not directly related to propulsion, as well as auxiliary electric devices like lights, heaters, and air conditioners. These are the grayish elements. WAN vehicles require no parasitic devices. All WAN auxiliary devices have low power demands. The bluish elements reflect the actual work done in propelling the vehicle. That includes energy expended during cruising and accelerating. Cruising involves overcoming the forces of air drag and rolling resistance. The EPA images refer to air drag as wind resistance. Rolling resistance can be thought of as the friction between the wheels and the road or tracks. During braking, the kinetic energy built up during accelerations is lost as heat. For hybrid and electric vehicles, the energy of motion can be recovered during slowing using dynamic braking, which switches the motors into a generator mode that can recharge batteries. This is reflected here by the bright green elements with negative energy consumption. Note that the propulsion work energy consumptions are roughly the same between the different powertrain types within each city and highway group. That is because these are determined by the mass, frontal area, and coefficients of drag and rolling resistance. Those parameters are generally consistent across powertrains. The values vary far more based on whether the vehicle is a car or a small truck, as well as the subtype within those types. City driving propulsion work is dominated by braking losses due to the high rate of stops requiring energy-consuming accelerations. This is where the benefits of dynamic braking are felt most. The highway trip consumption is dominated by air drag costs due to the 2 times higher cruising speeds and the infrequent stops. Rolling resistance consumption is fairly consistent across all usage domains. For the rest of this discussion, we rely on the formulas in this table for the forces of air drag, rolling resistance, and acceleration. The power to produce those forces is equal to the product of the force magnitude and the vehicle speed. This is particularly important for air drag, where the power requirements then grow as the cube of the speed. The 2 columns on the right compare WAN and CUTs parameter values in each area. CUTs vehicles are partitioned into cars and small trucks, as those have very different values for the main parameters. Two factors of air drag we can control for all speeds are the frontal area and the coefficient of air drag. The frontal area dimensions of WAN vehicles are entirely determined by what is comfortable for a single person, as the passengers are seated in line. This provides the minimal frontal area for a vehicle carrying people seated comfortably. WAN vehicle frontal areas are about 1 square meter. CUTS car frontal areas in our sample average about 2.3 square meters, with small trucks at about 3. The main components of the drag coefficient for road and individual WAN vehicles are the aerodynamics of the shape, also known as form drag, the skin friction, and the effects of protrusions like wheels. We will discuss this in more detail soon in the context of WAN trains, where we justify a value of 0.09 for intercity WAN vehicles and 0.08 for non-intercity ones. CUTS car coefficients of drag in our sample average about 0.31, with small trucks at about 0.37. A concerted global effort should be able to optimize the vehicle drag coefficient for the WAN deployment. We discuss that shortly in the context of dynamic trains of WAN vehicles. The product of the frontal area and the coefficient of drag for CUTS cars is about 8 times greater than WAN vehicles. For small trucks, the WAN advantage grows to about 13. The force needed to overcome rolling resistance grows linearly with the fully loaded vehicle mass. WAN vehicles are limited to cargoes with a mass no more than 2 large adults. WAN intercity vehicles have a fully loaded mass of about 400 kilograms. The maximum for non-intercity vehicles is about 300 kilograms. The CUTS car masses in our sample with similar cargo masses average about 1,600 kilograms, with small trucks at about 2,200. WAN would provide a much lower coefficient of rolling resistance than CUTS road vehicles. The track surface on which the WAN bogie wheels ride would be very smooth. The wheels would be tubeless and very smooth. Smooth tubeless wheels on smooth tracks have a coefficient of rolling resistance of 0.001. CUTS car tires on typical road surfaces have coefficients in the range of 0.006 to 0.015. Even for the same tires, the values vary with road surface and tire pressure. A fully loaded WAN vehicle would then have a rolling resistance force of about 3 to 4 newtons. That force for the CUTS cars and small trucks would be 30 to 75 and 36 to 90 times larger, respectively. The result is that while rolling resistance consistently accounts for about 25% of the CUTS vehicle propulsion energy consumption, it is largely irrelevant for WAN. That is particularly true as the speed increases. The power required for any acceleration rate at all speeds would be about 5 times smaller for a fully loaded WAN vehicle than a CUTS car, and 7 times less than a small truck with the same load. This is important in limiting the powertrain demands during WAN vehicle track switches. In addition, WAN vehicles for urban trips would only have 1 acceleration from stop per trip, and typically 0 to 2 partial accelerations coming out of turns. CUTS vehicles perform many accelerations per urban trip, and it is those that cause the high city braking energy losses. Electric and hybrid vehicles do recover some of that with dynamic braking. WAN could also do that, but it is questionable if the benefit would be worth the complexity. Note that all these comparisons apply independent of the CUTS vehicle powertrains. For CUTS internal combustion vehicles, the WAN advantage would be increased by another factor of 3 to 4 by the efficiency of the electric powertrain. It is that factor and the dynamic braking which gives CUTS EVs their large efficiency advantage over internal combustion vehicles. However, a little of that EV advantage is lost due to the high mass of the CUTS EV battery packs. This table lists the various WAN guideway types and 14 movement tracks, along with the speeds in both meters per second and kilometers per hour, as well as the minimum headways and throughput on each track. The cruising energy consumption and power rates are also provided. The energy and power rates were determined using the equations specified earlier, assuming a 10% loss during battery charging and a powertrain efficiency of 85%. Those are based on the typical numbers for EVs. The same calculations were done for all vehicles in our dataset, using the parameters found in the time versus speed data of the 2 EPA driving cycles. The results of that are available online. We have not mentioned LAN, as its vehicle fleet would consume less than 5% of the energy of the WAN fleet. That is because with average trip lengths over 20 kilometers, their fraction of the trip would average less than 5%. Further, the vehicles move slowly and are even smaller and lighter than the WAN ones. As a reference, the best EV cars in our dataset had EPA-reported ECRs of about 600 to 700 kilojoules per kilometer for the city and highway driving cycles. Those cycles reflect average speeds of about 30 and 85 kilometers per hour, respectively. Note that the only tracks that operate even close to such slow speeds are the slowest arterial ones. Those have consumption rates 8 to 10% of the EV rates while moving faster. The consumptions on the intercity tracks are far greater. All are reduced further using a dynamic train mechanism discussed soon. The WAN vehicle ECR advantage is partially offset by the smaller cargo capacities than the corresponding CUTS vehicles. So far we have discussed vehicle kilometer ECRs. We are really interested in the energy per passenger kilometer and for goods to some degree the ton kilometers. For passengers the difference is small. The passengers per vehicle, also known as the load factors, for CUTS cars and small trucks are 1.5 and 1.8 respectively. The WAN load factor would exceed 1.3. Also, as we shall soon see, transit buses in the US actually require more energy per passenger than the personal vehicles. For freight, the small cargo capacity and the corresponding increase in the number of vehicles needed to carry a given load is a potential issue. This is not that much of a concern relative to the freight carrying uses of CUTS personal vehicles. These seldom carry loads that would not fit in a single WAN vehicle, and such trips would mostly occur on the slowest IS and arterial tracks, where the ECRs are very low. For such small loads, we are not concerned with the energy cost per ton kilometer, but the vehicle level consumption. The issue is more related to freight moved by commercial vehicles that have capacities from 3 to 60 tons, with railcars carrying even more. There is a trade-off here between energy demand and vehicle counts that we will discuss shortly. But first we discuss WAN dynamic trains that reduce the average WAN vehicle ECRs even further. The WAN dynamic train mechanism is a simple extension of the dynamic coupling mechanism used between vehicle modules. Forming a train is mostly just a matter of one vehicle catching up to another and matching speeds. This could happen on most vehicle track switches. CUTS vehicles emphasize a safe following distance. WAN vehicles try to join with other vehicles immediately ahead or behind. Vehicles carrying only goods would often enter and stop on a loop track. They then wait for another vehicle or train to approach so that they can enter the moving track and perform the coupling. The forces on trains add a few more details to the basic air drag and rolling resistance model used earlier. These are generally expressed using the Davis equation as given in this table. The numeric values and the parameters were mostly produced from empirical studies of certain trains by Armstrong and Swift. The WAN column expresses the values we use for our WAN ECR calculations. The main differences with the individual vehicle model are the introduction of two new elements that are linear with the vehicle speed. There is also a split of the air drag coefficient into form, skin friction, and 3 protrusion elements indicated in blue. The speed is also distinguished between ground speed and airspeed. For WAN, the covers provide isolation from the wind, eliminating the need for that distinction. The speed linear terms are largely irrelevant for WAN trains due to its batteries with low-power electric powertrain. That also eliminates the need for pantographs to supply the electricity. There are simple mechanisms that would make for smooth gaps between vehicles in a WAN train. We are then left with the form, skin friction, and bogie components of the air drag coefficient. The form factor is independent of the train length. It is, however, significant for individual vehicles or trains of 2 vehicles. We assume the WAN vehicle nose and tail would be of near optimal shapes. The sole protrusion from the shell would be the very short poles going into bogies running on the track. This is reflected in the 0.05 value used for the nose and tail drag term. The frontal area is restricted as noted earlier by the choice to have a hole fitted to 2 adults sitting in line. Various options have been explored that should be able to eliminate bogie drag effects from all but the lead bogie. That again means that the bogie drag is largely independent of the train length. The area of the bogie is very small, and the shape again would be near optimal. That would limit the impact of bogies for trains of 1 or 2 vehicles. The biggest factor left is the skin friction. This is proportional to the surface area of the train shell. That grows linearly with the train length. We assume the Armstrong and Swift constant for our base calculations. This chart presents how the drag per vehicle decreases with increasing train length. The two upper lines reflect the performance for the WAN intercity and non-intercity vehicles, using all the numeric values in the table. The lower two lines reflect what the specified reductions in the skin friction coefficient would produce. In all cases, note that there is little efficiency gained in having more than 5 vehicles in a train. However, there is little penalty, and there is a track capacity increase. The overall vehicle, passenger, and freight ECRs for all the WAN tracks are presented in this chart. We have also provided the numbers for the average CUTS EV vehicle rates to provide a reference. For CUTS internal combustion vehicles, the vehicle kilojoule per kilometer rates are over 4,000 for city driving and 3,000 for highway driving. These are not shown as that would compress the other values too much. WAN freight trains travel almost exclusively on the lowest speed tracks for each guideway type. However, even with the larger capacity of the intercity vehicles, the energy consumption per ton kilometer is significant. We will see the fleet effects of that shortly. Note that longer trains do support higher vehicle throughput capacities on each track. Even with the train lengths assumed, all intercity tracks have capacities over 10,000 vehicles and 3,000 tons per hour. We are interested in the overall fleet demands for passengers and freight. This chart provides a comparison of WAN passenger rates to those of the various CUTS passenger modes. In terms of passenger kilojoule per kilometer, closest CUTS mode to non-intercity WAN is transit rail. What may be surprising to many is that transit buses are actually worse than either cars or small trucks. The reasons for this are the relative size of the bus, the very frequent stops, and the large mass which together produce large acceleration braking losses, and the low average bus load factor in the US. In other countries, bus load factors are higher, but on all transit networks, for a substantial part of the day, a bus will have low load factors. Hybrid powertrains with dynamic braking would be a big benefit for buses. WAN intercity would replace the domestic commercial air and intercity trains. In the US, most of those passenger kilometers use flights, and the consumption rate for that is about 3 times the intercity WAN rates. Although the plane's top speed is higher, except for long direct flights, WAN trips would also take less time. Overall, because of the big advantage relative to internal combustion personal vehicles, the US CUTS passenger fleet would consume about 11 times that of the WAN fleet. Further, all of this would use electricity produced from renewable sources built as part of the WAN deployment. Freight handling is the one area for nets where there are serious trade-offs that need to be made. This is illustrated in this chart that compares the freight energy consumptions as well as the number of vehicles. The trade-off concerns the number of WAN vehicles of the two types, the total amount of energy required, and what to do about rail freight. The CUTS truck fleet is partitioned into single unit and combination trucks. The latter mostly perform long-haul trucking, while the former deal with goods in urban and nearby rural areas. Both carry far more goods per vehicle than WAN, but they also consume far more energy, with average vehicle ECRs of 11,000 to 14,000 kilojoules per kilometer. We assume that non-intercity WAN vehicles, traveling mostly on the slowest IS and OS arterial tracks, would replace the single-unit truck trip. They have a nearly 10-to-1 advantage in kilojoules per ton kilometer. However, they need more than 2 times as many vehicles. That ratio is that low because they are each available at all times. In contrast, the average single-unit truck averages less than 130 kilometers per day. Intercity WAN vehicles would be used to replace the combination trucks. The WAN vehicles consume much more energy than the non-intercity vehicle per vehicle kilometer due to their relatively higher speed. However, that allows them to move the goods more quickly. The net benefit in kilojoules per ton kilometer is only about 3.5 relative to the combination trucks. However, because they are available for more of the day and travel faster, the number of additional vehicles is only about 1.5 times. The big trade-off comes with respect to rail. CUTS trains have about the same freight ECR as WAN non-intercity vehicles. but their huge capacity means that more vehicles would be required than the total of the truck replacements. Much of the rail cargo is bulk goods like coal. There are then questions as to whether WAN should just keep using rail for such goods. Also, should we use intercity vehicles for parts of those goods to trade off the extra energy consumption to reduce the number of WAN vehicles required? The answer to this comes down to the relative cost of the energy versus the vehicles. The energy cost is our next topic. Also, as we will describe later, in a nets world, much of the demand for freight shipments will be significantly diminished.